All right, so this is part 10, the last part to Unit 2. And in this video, we are looking at word problems and modeling with exponential and logarithmic functions. So in this first type of example we're going to be using these formulas here. And what these represent, they're the exact same formula. If you look at the formula here, it's just the first part that's a little bit different. It means the same thing. I'm going to just reference this one. This A here represents what's called the accumulated value. So we're going to be looking at like money in accounts over time, or fossils decaying, or population growing, and that will be what is left after a certain period of time. This A sub 0, this is called A naught. This is the initial value. So if we're talking about like putting money into account, that would be how much money you're putting in. Or if we're looking at population growth over time, this would be the initial population. If we're talking about like a fossil, we're talking about how much of like carbon-14 you start with. So that's what's called the initial value. And then E is just the number E, so that 2.71 that we've been using for this whole chapter, or this whole unit. And then K is a rate, so maybe like a rate that something is decaying, or the rate at which population is growing. And then T is representing time. Now, if that K value is greater than 0, then that means that this is a growth, and if it's less than 0, it's a decay. The first example we're going to look at is population growth. I have no idea if these numbers are like true numbers from 1970 and 2007, but we'll use them anyway. It says in 1970, the U.S. population was 203.3 million. By 2007, it had grown to 300.9 million. Find an exponential model or exponential growth function that models the data for 1970 through 2007. So we're going to be using that formula right here. So I'll just go ahead and write it over here. A equals A naught E to the KT power. And it tells us our initial population. So think of 1970 as T equals 0. No time has passed yet. 2007 then would be 37 years later. So 2007 would be T equals 37. So our initial population, that A naught, was 203.3 million, 203.3, and we can just use it as that number. And then after 37 years, it grew to 300.9 million. And then E, and we don't know the rate. That's what we're going to be trying to solve for, but we know that 37 years passed in that time. And so this is just like the equations we were solving in part 9 video. So we want to try and solve for K. So the first thing I need to do is get rid of this coefficient on the E. So I'm going to divide both sides by 203.3. 203.3. And that's gone now. And then I have 300.9 over 203.3 e to the KT power. So what I'm going to do then is take the natural log of both sides. So I have the natural log of 300.9 over 203.3 equal to, and the natural log of e to the k to the 37 power, well, the natural log of e will cancel, and I'll just have k times 37. So I can divide both sides by 37, and k is equal to the natural log of 300.9 over 203.3, and that whole thing divided by 37. So make sure you're using parentheses when you're typing that in your calculator. And when we type that in our calculator, you should get 0.0106. And so that's our rate. Now, part A said find an exponential growth function. So A equals 203.3 e to the 0.06 or 0106 t power, and that would be our equation. The next example, or the next part to that example, says, by which year will the U.S. population reach 315 million? So this is telling me an accumulated value after a certain amount of time. We're solving for t. how many years after 1970. So 315 equals 203.3 e to the 0.0106 t power. And we're basically doing the same thing we just did. We're going to solve for, this time, t. And then again, I'll take the natural log of both sides. And then we'll have the natural log of 315 over 203.3 equals, natural log of e cancels, and we have 0.0106 t. If I divide both sides by that, then t is equal to natural log of 315 over 203.3 over 0.0106. Typing that on my calculator, we get 41.3. Now, first, I want you to write the exact answer in these types of questions too. In part 9 of the videos, I mentioned that I wanted to see your exact answer and your rounded answer. Same thing for the word problems, exact answer and rounded answer. Now, this is not the year. It says by which year. This tells me how many years after 1970. Now, this is 41.3. So after 41 years exactly, it's not quite at 315 million. It would be the following year, which would be rounded to 42 years then after 1970. So that would be by 2012. In any type of word problems, you want to make sure that you always answer the question that is actually being asked. So for the next type of question we're going to look at, we're going to be looking at half-life, and this is looking at fossils decaying. So half-life is the amount of time it takes for half of a sample to disintegrate. Half-life is used for a number of things, not just fossils. It's also used for like medication. So let's say you take Tylenol and they tell you that you can take it every 6 hours. They're measuring how long it takes Tylenol to disintegrate in your body and kind of work its way out. They might measure the half-life, meaning how long it takes for half of the amount of Tylenol you took to leave your body. And it might be maybe 4 hours for Tylenol to have left your body. So that's what we're looking at here. And so we have in this case, fossils, and it says, use the fact that after 5,715 years, a given amount of carbon-14 will have decayed to half the original amount. Find the exponential decay model for carbon-14. Now we're going to use that same formula, A equals A naught e to the kt power. And it doesn't tell me my initial value, but it does tell me that after this many years, I'll have half of that initial value. So I can write half of the initial value, and whatever that initial value was, e to the k, which we don't know, and then t was after this many years, 5,715. Now, we don't know what A naught is, but whatever it is, let's say it was, 20, or I have no idea what number we could have it represent. We can divide both sides by that number and it cancels out. So now I have 1/2 equals e to the k times 5,715 power. And we can go ahead and take the natural log of both sides. Again, the natural log and e cancel, and I have the natural log of 1/2. I can divide by 5,715 on both sides, and k is equal to the natural log of 1/2 over 5,715. Typing that in my calculator, we get negative 0.000121. Now we have a negative value, and that's because the amount of carbon-14 is decaying. It's not getting bigger, so this is a decay function. Now the question said to find an exponential decay model. So we want to write an equation. That would be A is equal to A naught e to the negative 0.000121 t power. In the next example, we're using that equation. It says in 1947, earthenware jars containing what are known as the Dead Sea Scrolls were found by an Arab Bedouin herdsman. And analysis indicated that the scroll wrappings contained 76% of their original carbon-14. So we're going to use that. And it says estimate the age of the Dead Sea Scrolls. So we're going to use that formula that we just created here. And it doesn't tell us how much is left, the accumulated value, but it says that there's 76% of the original amount of carbon-14. So we don't know the original amount, we don't know the accumulated value, but we know that whatever that original amount was, there's 76% of it left. So the way we can write that is 0.76 times A naught. So there's 76% left. And then negative 0.000121 t power. And then again, we can divide or solve for t. So we can divide both sides by a naught. Those cancel out. We can take the natural log of both sides again. The natural log and e cancel out here, and we have the natural log of 0.76 equal to negative 0.000121 t. Divide by that on both sides. And t is equal to the natural log of 0.76 over negative 0.000121. Okay. And we can go ahead and type that in our calculator, and that would give us 2268.07. So that doesn't tell us what year, but it says estimate the age of the Dead Sea Scrolls. And it says that they were found in 1947 with 76% of the original carbon-14. So what we could say then is that in 1947, they were 2,268 years old. Okay. All right, moving on to the next type of example, we're going to look at some log word problems here. And here it says that we're looking at some log growth models. And what's nice about these problems is that it actually typically gives you the equation. So you can see in our first example here, it says the function f of t equals 30,000 over 1 plus 30e to the negative 1.5t, and it describes the number of people, f of t, who have become ill with influenza, or the flu, t weeks after its initial outbreak in a town with 30,000 people. So this formula is already given here. Let's talk about what each part of it means. A, B, and C are constants. C and B have to be positive, and this C value is called the limiting value. It's the maximum amount of growth, essentially. So going back to the example that we just read, let's see here. The first part says, how many people became ill with the flu when the epidemic began? Now again, T is representing time. T weeks, and when the epidemic began, no time had passed, so that's when T equals 0. Well, for A, if we find f of 0, essentially plugging in 0 for T, that would be 30,000 over 1 plus 30e, and then negative 1.5 times 0. Well, negative 1.5 times 0 is 0. E to the 0 power is just 1. 1 times 30 is 30. And then 1 plus 30 is 31. So 30,000 divided by 31 is about 968. So at week 0, meaning no time had passed at all, when the epidemic starts, 968 people are sick with the flu. Part B, how many people were ill by the end of the 4th week? So finding f of 4. Well, same formula, 30,000 over 1 plus 30 times e to the negative 1.5 times 4. And when we type that into our calculator, we get about 27,924. So there's 30,000 people in the city or in the town, and after 4 weeks, 27,924, almost 28,000 people have gotten the flu. So it doesn't take long for it to spread that fast. And, with life in a pandemic not that long ago, we can see how quickly it spread in real life then. C says, what is the limiting size of F of T, the population that becomes ill? Well, the limiting size is the maximum amount of people who could become ill. Well, if a town has 30,000 people, you can't have more than 30,000 get sick. So that means the limiting size is 30,000 people. You can't have more than that, more than the amount of people you have get sick. All right. We have one more type of problem we're going to look at, and this is heating and cooling. This is Newton's law of cooling here, and this is that formula you see at the top here. T represents the temperature of an object after a certain amount of time. C represents the temperature of the surrounding medium. So for example, if you have a cup of ice and you put it in a room that's 75 degrees, the surrounding medium would be the room that's 75 degrees. T naught, or T sub 0, is the initial temperature of the object you're measuring. So in the example I just gave, that would be the temperature of the cup of ice. And C here is the same C here, that surrounding medium. K is the rate, E is the number E, and little t is time. So we're going to look at an example here. It says a cake removed from the oven has a temperature of 210 degrees Fahrenheit. It is left to cool in a room that has a temperature of 70 degrees Fahrenheit. After 30 minutes, the temperature of the cake is 140 degrees. So a cake removed from the oven has a temperature of 210. That's the initial temperature of the cake. 30 minutes would be our little t, the amount of time. 70 degrees is the temperature of the room, the surrounding medium, so that would be C. And then after 30 minutes, the temperature of the cake is 140. That would be T, big T, the temperature after a certain period of time. So part A says, use Newton's law of cooling to find a model for the temperature of the cake, big T, after little t minutes. So 140 equals 70 plus 210 minus 70, e to the k times 30 power. So condensing these numbers here, 210 minus 70 is 140. Subtracting 70 from both sides, this becomes 70 equals 140 e to the k times 30 power. From there, we can divide both sides by 140. This is going to look a lot like the problems we started out with in this video. 70 over 140 reduces to 1/2 equals e to the 30k power. We can take the natural log of both sides. Natural log and e cancel. And then I have the natural log of 1/2. I can divide by 30 on both sides. And that equals k. And typing that into my calculator, we end up with negative 0.023. So then the formula, or the model that we're looking to write, would be T equals 70 plus 210 minus 70 e to the negative 0.023 t power. All right, so that's for part A. Part B says, what is the temperature of the cake after 40 minutes? So part B, we want to know what the temperature is after 40 minutes. So that's 70 plus 210 minus 70 e to the negative 0.023 and 40 minutes. So typing that into our calculator, we get approximately 125.8 degrees Fahrenheit. And part C says, when will the temperature of the cake be 90 degrees Fahrenheit? So they're telling us an accumulated value temperature. And then they want us to find how long until it reaches that temperature. So how long do you have to wait until it's cool enough to eat? So we have 90 equals 70 plus 210 minus 70 e to the negative 0.023 t power. I can condense these two. I can subtract 70, and I get 20 is equal to 140 e to the negative 0.023 t power. And then I can divide by 140 on both sides. 20 divided by 140 is 1/7. I can take the natural log of both sides, and again the natural log and e cancel, and I can divide by negative 0.023. So I have ln of 1/7 over negative 0.023 is equal to t. Typing that in my calculator, I get 85 minutes. So I'd have to wait about 85 minutes for it to cool down to 90 degrees. And that brings us to the end of part 10 and the end of unit 2.